Hello and welcome to IEEE Soft Robotics podcast. In this podcast, we're going to interview researchers from both academia and industry about their work, thoughts, spectrum, and more beyond that. This is Marwa ElDiwiny, and I hope you will find this podcast useful. If you would like to connect with us, simply send us, and we will be happy to hear from you. And here is my interview. Thanks.
Hello and welcome to IEEE Soft Robotics podcast. Hello, Robert. Thanks so much for joining us in the podcast. I would like to ask you first how you would like to define yourself for the audience who may be first time listening to you.
I'm an origami artist and consultant.
So I think many people know about how your work is really fascinating and inspiring. But before diving to origami, I would like to go for childhood, because in each episode we ask about the childhood. And I'm curious about your childhood, how it was being interested in science, or what kind of childhood do you have?
So my childhood, I was very interested in nature, and of course, very interested in origami my whole life. I started origami at the age of 6, and it's been a hobby and a passion my whole life. And in high school, I became very interested in mathematics. And in fact, was on high school math team and did competitions, and thought I might become a professional mathematician. Mm-hmm. But then when I got to Caltech, during my freshman year, taking the various survey courses in different fields, I took an electrical engineering course in digital electronics and found that really interesting and fun. So I decided to major in electrical engineering. And so that is, of course, what led me to the field that brings me to IEEE.
Podcast. Yeah, I saw you're still involved. So I'm curious about the point, because you quit your job a couple of years ago, and as I read from your letter, that origami was kind of escape for you. I wanted to see how this point, because I think maybe people could resonate with that when you have a passion for something, or maybe you want to do something, but you're stuck in something maybe is not fulfilling. If you can tell us about this transition to get a decision and leave and do a...
Sure. I did find lasers and optoelectronics, which was my professional field, fulfilling, particularly the technical aspects of research. I mean, when I was a working scientist, that was just incredibly fun. I worked at JPL, and then I worked for about 10 years at SDL, a manufacturer of diode lasers, in various roles doing R&D, and then over the years moved into various levels of management, where I was not doing the technical work myself, managing others, and I mean, that was still satisfying, but not in the same way as hands-on technology. But origami throughout this whole thing was hands-on and stayed very satisfying. And I pursued it nights and evenings and weekends, writing books about collections of recipes for how to fold different designs that I'd come up with. But throughout pretty much my whole laser career, I'd had an idea for a book that I felt was needed and that I could write, which was a book about how to design. So people would not just follow the instructions for my designs, but they could come up with their own designs. And I worked on this book off and on, but never really making headway, and finally came to the conclusion that the only way it was going to get written was if that was my total focus for a year or two, however long it took to take, and that was incompatible with having a full-time day job in optoelectronics. So the trigger of making this transition was weighing those two choices. Do I continue down the path of optoelectronics, the conventional path, or do I try something different that allows me to write this book? And I felt like, there's a lot of engineers in the world that whatever I didn't do in engineering, someone else could do, but I did feel like I was the only person who could write this book and that it was an important book to be written. So that was the trigger. I quit my job, started working on the book, and also hung out my shingle for other origami related work. And over the time it took me to finish the book, I developed enough projects, consulting, lecturing, teaching, and so forth, that the origami became a successful career. And it was really fun and satisfying. So basically, I just never went back.
Yeah, good for you there.
But one of the unexpected things in the origami career was a lot of those opportunities turned out to be very technical as well. Highly mathematical, lots of engineering, theoretical modeling related to the design aspects of engineering. So although I hadn't expected it, it turned out that life still scratches the itch to design, to do math, to do theoretical modeling. So in the origami world, I get it all, both the art and the science.
Wonderful. So I'm curious about the origami. First of all, what's something is very beautiful and it's very hard to understand when it comes to shapes and designing? What's something very inspiring? You get inspiration, for example, you have a lot of shapes and very complex. So the inspiration to do that, from which point you have to start and how you translate that with the mass or the model. If you can tell us about, because it's very interesting what you do about this correlation from the mass to generating these designs.
Yep. And that question was the thing that inspired this book. The idea of how do you start with a design goal and then go through a series of steps to achieve that goal. And in engineering, very often the first step in that process is to figure out how to describe our problem in mathematical language, whether it's electronics or optics or mechanics or something. If we can describe the field and the problem and the constraints in the language of mathematics, then we can use the tools of math to solve the equations, to perform the optimization, to tell us what to do, to create a plan to follow, to create the object or structure that we're trying to create. And so a lot of my work during the kind of 10-year period in the 90s was figuring out how to translate the design goals in origami into mathematical language. And it turned out to be very, very successful, to work very well, establishing a conceptual link between ideas like flaps that make appendages, arms and legs, and how long they are, and how connected they are, to purely geometric structures, circles and wavy shapes we call rivers and polygons, and rules about how close they can touch each other within the crease pattern, or how close they can come. They can't overlap, they can touch, they must touch. And we can translate the problem of designing a specific origami figure into a purely geometric problem of packing different shapes into a square. And those shapes that we pack are arrangements of lines that ultimately turn into the creases that we'll be folding on.
Mm-hmm. That's interesting. So when it comes to inspiration, is this something was hard to transfer into geometric modeling when it comes, because modeling also is so hard when you model something? Just is this something example was really challenging to make origami design an inspiration, or yeah, something you out of the blue that's to come to you, I want to do something different? Do you have any scenario like that?
Yeah, there is, and it's perhaps one of the most still currently frustrating or challenging aspects of origami, which is that we can translate structural information, lengths and widths, thicknesses, numbers of layers. These are all things that can be translated into mathematical terms. But aesthetic properties, whether something is beautiful or not, whether it makes an emotional connection to us, we don't know yet how to translate that into math. And so when we're doing origami art, what we're most focused on are the aesthetic aspects. And we can't write down equations for as something beautiful or thought-provoking. So the best approximation we can do is to think of the structural description that will be beautiful or thought-provoking. Do that translation, do the design, fold it, create the shape, and then hope that it achieves the aesthetic goal that we set out to do when we define the structure.
Mm-hmm. If there's any something else you think still missing when it comes to either in the art or maybe in the science of mathematics or origami, is something you think still missing?
Oh, there are many things
Maybe
missing. In particular, whenever we come up with a mathematical design algorithm, it only works for a particular class of shapes. So for example, the tree theory, which is the body of work that I developed and wrote a program called Tree Maker to describe, that works for the class of shapes that is roughly tree-like, that can be described by a tree graph, or you can think of it as something that has lots of long, relatively slender appendages. So it works great for things like insects and spiders and so forth. And we'd say maybe works okay for things, let's say, like dogs and cats, except if we reduce a dog and a cat to a tree graph, to a line drawing, it's the same, it's basically the same stick figure for both a dog and a cat. And yet there are definite differences we need to make in the folds to make one look like a dog, one look like a cat. And so what's missing would be the mathematical description that lets us make that distinction back in the design stages. And then there are shapes that are just totally not appendage oriented. If I wanted to create an origami cloud, or even, let's say, an elephant or hippo that's mostly round, or an origami amoeba, or something close to home, a coronavirus, round with little spikes sticking out of it, that's not a tree-like shape. And so the mathematical algorithm for tree theory is not going to work at all on that type of shape. Now, there are other mathematical algorithms, and in fact, there are mathematical techniques for creating polyhedral shapes that would, for example, work pretty well for a coronavirus. But still other shapes that don't work. One of the big challenging areas right now is how to design shapes where both the surfaces and the fold lines are curved. And there's mathematical theory being worked out for that, and people are developing computational plugins for architectural programs like Rhino and Grasshopper to do that. But this is still in the early stages. And then there's a whole level of phenomena that are not yet adequately modeled, like taking into account the thickness of the material and in energy-based properties like springiness and differences between elastic and inelastic deformations. And there's not a lot of theory that incorporates those effects, but those can be important. And especially when we start applying origami to technology, like space structures in medicine, those effects become very, very important.
I can't agree more with that. I think that's very interesting and very important, even soft robotics, because we don't have a methodology how we can incorporate the shape or topology as well in the design. So we'll go for that for sure. It's very interesting. But for the shape again, because I saw that most of if I understood that, it's boiled down to square or circles or just basic shapes at the end of the day, if it's right. Do you have any kind of maybe complex shape that to design something you do need a square? I mean it, for example, linear or non-linear shape, for example. Do you have something that, whether you have to go for linear shape or non-linear shape, the basic component to make the structure? How you figure out that's need linear or non-linear shape or both, and how that make difference in the design?
Okay, so the building blocks aren't necessarily linear. I mean, usually the building blocks are actually 2D shapes like polygons, and they can be circles, they can be squares, they can be rectilinear, they can be hexagonal geometry like hexagons and triangles. There are design rules that cover all of those. And one of the areas that I'm that I'm actually working on right now in collaboration with a couple of mathematicians is design rules where we're actually creating the design in a four-dimensional hyperspace, that this four-dimensional space is sort of the natural place to do all the design work, and then we'll project it down into a two-dimensional sheet of paper. The other thing to keep in mind is that although traditionally origami has used paper, and traditionally that paper has been a flat sheet, we can imagine, and not just imagine, we can carry out origami with materials that behave very differently from paper: metal, wood, polymers, graphene, carbon nanotube mats, and the like. And similarly, we can use surfaces that are not flat. One can do origami with spherical paper, or a spherical sheet, or hyperbolic sheet. And of course, then the mathematicians in the world say, well, what are the rules of origami in spaces that can't even exist in the real world, like in elliptic geometry, where the North and South Pole are the same point, or in some higher dimensional space, folding a 3D space in 4 dimensions, for example. And although that sounds pretty impractical and unreasonable, it actually turns out to have an application. That there's cosmologists have found that the evolution of dark matter in 3 dimensions folds into sheets, or folds into shapes that are analogous to origami fold patterns. But now what's being folded is a 3-dimensional dark matter region rather than a 2-dimensional sheet.
That's interesting. Yeah. So maybe I'll go to again for the application, because you have been involved in a lot of industry application about that. And you mentioned, for example, thickness and the material. And if we want to combine, for example, different material in that case, can you tell us about the challenges here? What could be limitation maybe when it comes to origami with designing different material? And yeah, taking account we need real application here. So how it goes here? What's a challenging or limitation here?
So one of the first things to consider is that the application is going to constrain our choice of materials. If it's going into space, it has to be space qualified material, something that can withstand the temperature extremes and radiation environment and the like. If it's going into if it's medical, if it's going into the body, then it has to be a biocompatible material. So something that's, that's not going to be toxic. Yeah. And then the application might also demand mechanical properties that can only be met by certain materials in terms of certain stiffnesses, compliance, mass density, things like that. And so when we have those constraints, we need to look at the properties of those materials and realize that very often they're quite different from paper. And so it differs from our experience, from if we've been working with paper, as I and many other origami artists have. And a really good example, a very simple example, is just the process of creating a crease. Paper is a unique material in that if I fold it one way and then unfold it, then I've created a line of weakness, and the paper will naturally easily fold in the other direction in the exact same place. And that's actually very unusual. If we take metal or plastic, first, if we start to fold it, it'll stay in the elastic regime and spring back. And if we fold it all the way so that we've forced it to undergo inelastic deformation and then unfold it, the inelastic deformation will create a permanent crease that only wants to go the direction we originally folded it. If we try to fold it the other direction, it will in fact try to create a new crease in a new place next to the old crease, but anywhere except where we made the crease. And if we were working with metal, we have the problem that when we made that fold, it quite likely underwent work hardening. So it won't unfold or it might now be more brittle and more liable to break. So all of these properties are very material specific. The application will drive us to a certain set of materials, and then we need to take into account how those materials behave that may be very different from the materials we're used to.
Yeah, that's very important point and very interesting when it comes to material selection. For example, in the space application, for example, you can tell us about the design thought process, because I saw that sometimes it take from you like a couple of months and sometimes to make a design and even more. But when it comes to industry or application, do you think how we can use, for example, simulation tool, or because the modeling sometimes is just limitation, and don't invest a lot of time in making the design by your hand and origami? And yeah, do you have any insights before you embarking in the designing by, for example, in a space application? How the process is, to figure out whether this design would work or not, or whether I have to get something beyond what we have inspiration from nature, something, artificial, for example, inspiration,
So there's always a stage, usually in the early stage, where we rely on our intuition, and experience and intuition. That's engineers. We'll start with that just to have a general idea of how to go about that.
Mm-hmm.
And if we have some background in origami or folding, we'll draw upon those ideas from that background. But in almost everything in industry and absolutely in space, there's going to come to a point where we need to use the tools of that industry to really probe the design, maybe to refine it in terms of final dimensions or which materials work, or just to learn its performance. And so at that point, we might have made a paper model of a solar array, but at some point we're going to have to put it into, for example, a finite element analysis program and look at what the stresses and strains really are when it's subjected to the sorts of forces and motions that it's going to undergo in the application. So there is this transition that happens going from our intuition, our brain, our pencil and paper sketches, maybe nowadays our drawings on a pad, but it's still sketches, that go into the professional level tools that are used in the industry that's actually going to be using this thing.
Mm-hmm. Do you have something like that happen that you saw that you have to design in a certain way, but you figure out this wasn't right to be designed this way, or maybe something you didn't expect it, or counterintuitive to where you already mentioned that it's based in intuition? Is this something was counterintuitive to you when it comes to designing the origami? How does this happen?
Yeah, in a way, I'd say the examples of that are so numerous that it's hard to pin any one thing down. Because the whole idea of taking a design to the next level of stage is to discover the things you didn't realize were true, or to uncover your own misconceptions. And so pretty much every time I fold something, whether it's for art or for technology, there is some aspect of the folding that surprises me, that I didn't encounter. A really good and common example is effects of thickness, because most of the design mathematics of origami assumes zero thickness paper, because it just gives a very mathematically clean model. And if we're folding things from thin paper, a lot of our intuitive ideas are sort of based, we assume that the thickness can, for the most part, be neglected. But in many applications, it's very real. And there was a case where I was developing for a client. It was a container where the container itself could collapse down to a much smaller size. Think about the equivalent being like a cardboard box that collapses down to a flat state. And this was similar sort of problem. And so I designed the pattern with all the cut lines and the fold lines and so forth. But the first time I built it up, I saw, here's a few places where I didn't properly account for the thickness of the material. And so I need to shift the positions of a few lines to account for those positions, and so that's why we do design iteration.
Mm-hmm. Yeah, yeah. And maybe I'm curious to ask you, do you think about how we can take origami design to the next level? What could be something, yeah, I need to do it in a certain way, or you imagine it how it could be accessible? Because I don't know, do you think it's a talent or it takes intelligence for any, do you think anyone is entitled to do origami design, or it needs special people who are passionate about shapes and yeah.
Yeah, so my belief is that anyone can do origami design if they are given the tools to do so. And I think I've even proved that out in teaching. I've taught some courses where I took general audiences who didn't have any prior experience in origami, and over the course of a couple of weeks, introduced them to some of the simple design techniques. And by the end of those 2 weeks, people had a final project, which was to design something original using the techniques that they've learned. So now you might say that their designs bore similarities to what people had used before because they're using common design tools, but they were truly their own original designs. And these were general audiences, and so anyone can do that. I do think, though, that there is a difference between good origami and great origami. And more broadly, in art and engineering, there's a difference between good engineering and great engineering. And that difference requires some extra spark or talent or something like that, that goes beyond the basic tools of the trade. So I think that's true for origami, but it's true for many, many other fields as well.
Yeah, absolutely. Yeah. So maybe because about the art you do, as you are artists already. So I'm curious about what kind of feeling you have when you design this origami, and it takes a lot of time. I'm curious about the state of mind you have when you design them.
It's an emotional roller coaster because you do a design and at the end it's aesthetically unsatisfying. I got all the arms and legs and wings, but it just doesn't look right. And that's really disappointing, devastating. But then when it does look right, there's this tremendous sense of elation and satisfaction. And that extends to the mathematical and theoretical side. A lot of what I do is developing the theory of origami. And there's this when you discover something new in mathematics, there's this unique sense that you've discovered something that is universal. That a person on a planet going around another star, what I just discovered is as true for them as it is for me. They just might not know it yet, or they might have already known it for 1,000 years. But I discovered something universal, and at the moment of discovery, I'm the only person who knows that, and I want to share it. So we write a paper or make a posting on a mailing list to say, hey, guess what I learned, and that is really satisfying in its own way as well.
I really like this point where you say that you discovered something, maybe other people take 1,000 years to know about it. So do you think your ideas, for example, about origami or mathematical origami, you face sometimes that people don't understand, or there's misconceptions, or sometimes you feel that you didn't get the reaction you assume, that you're very passionate. So I don't know if you have any scenario like that, people don't understand what is mathematical origami, what you're doing.
Yeah, I do know that there are aspects of it that people don't understand, because there are aspects of it that I don't understand, and there's aspects of other people's work, even in origami that I don't understand, and I can try to educate them, or at least try to provide the tools by which they could learn and come to understanding. But they're under no obligation to understand, at least when we're talking about art. They're under no obligation, and they may not have an interest in that area. And that's totally okay if that's, you know, if that's how it works out. You sort of cast your bread upon the waters and see what comes up and finds it tasty and interesting.
Yeah. Absolutely, I agree with that. So we are going to end. I have a few questions. The first one, what's your aspiration as origami artist? And also you're already doing a lot of research. So you have both sides here. I think you're lucky to do both of them at the same time. So what are your aspirations?
Really, my only aspiration is to not have to stop. You know, and what I want to continue creating new and beautiful shapes that I find beautiful and interesting. I want to continue finding technological applications for what I do. I want to continue making mathematical discoveries. And I could imagine at some point, you know, the well running dry, just running out of ideas. And so my aspiration is no more than to not run out of ideas.
That's wonderful. Yeah. May I ask you, do you have any crazy ideas when it comes to technological application? You think about origami, or also, yeah, if any crazy idea just pops in your mind about origami, do you have any crazy ideas for application or designing? Yeah, something maybe still we don't have. Yeah.
Well, the craziest idea, which I've had for a couple of years, is it is unfortunately hard to describe. But some origami patterns display a particular very beautiful geometry in the angles at which the lines travel at. It's very pretty. And it leads to, I think, most of the art folds that people create using that geometry are also aesthetically interesting. And I would really like to develop the design rules or design system for creating that geometry. And I've been trying to do so for quite a long time and failing for quite a long time. It has led me to some interesting places like this higher dimensional thing I mentioned earlier in the interview that looks like it might be fruitful, but it might also fail. But it's worth pursuing. And you know, the craziest ideas that you pursue are the ones that are the most satisfying if they finally pan out. And that payoff makes it worth pursuing. I probably hasten to add that there needs to be a decent chance that it's going to pan out. I mean, we can pursue all sorts of crazy things that have absolutely no chance of ever working. So you need to temper the craziness with at least some plausibility.
Yeah, that's really thoughtful. Thanks for sharing that. But I think about the phase of the failure and how you overcome that to keep it, because you are extremely passionate about origami and the mathematics behind it. How you overcome this failure and what keeps you that there is a light at the end of the tunnel? How you achieve that?
You have to keep seeing the light. You know, the light at the end of the tunnel. As long as that light is still out there, it still beckons. And you know, and so as long as you feel like you're making progress, that keeps you going. So you have to have a little bit of optimism, I guess. But for me, I need to get the little drip, drip, drip of tiny successes to keep going. I mean, and sometimes on these ideas, the drip, drip, drip of successes stop, and I put it aside because I don't see any way of making further progress. I'm not going to beat my head against the wall. But very often, something that I've put aside, you know, that my brain continues to work on it in the background, and sometime later, might be overnight, it might be a year later, might be several years later, the brain's gonna pop out and say, here's a new approach. Why don't you try this? And then that gets the faucet going again a little bit.
Yeah, I really like this point. And may I ask you, what's the moment of inspiration for you? Because I know you're artists. Sometimes you need inspiration. What's the moment that you have this? I get this original design. How you make your mind crystal clear? Oh, I have this design. Is it a moment you have to be in the mood of get these original ideas? Yeah.
Yeah. So my inspiration tends to come from two very different places. For the figurate origami, representational work, and that looks like something, that inspiration often comes from nature. If I'm out in nature and I see an animal or something, and and I get this strong emotional reaction from seeing the animal, and I think I want to recreate that emotion in paper. I mean, that I want to recreate in paper something that gives me that emotional response. And then that's the inspiration. On the more geometric side, the inspiration very often comes from an abstract idea, like a class of shapes that I haven't seen and I'd like to create, and that requires the solution of a problem. For example, one from a couple of years ago was I wanted to make geometric patterns that fold flat, that unfold into a 3D shape smoothly with a single degree of freedom, and that had a more complex and interesting pattern to it than the currently known patterns. There's a pattern called Miura Ori. It's a tiling of parallelograms, and it has this property. There's some tilings of triangles, but I wanted to figure out patterns that had more interesting patterns, but still folded flat. And to do that, I didn't have a particular more interesting pattern in mind. I just wanted it to be somehow more interesting. And so that led to an exploration of what are the rules, what are the general rules for creating this shape, this type of shape, and to figure out what sorts of distances and angles I could define that I had control over, and what distances and angles were forced by mathematics to be what they were. And that would let me explore this large field of shape. And so I developed the theory and computer programs to explore the shape, and then I could find some interesting things by plugging in angles and distances and tinkering and saying, oh, that looks nice. I'll go fold one of those.
That's also inspiring. Thanks for sharing these points. Thank you. So, do you think ego is important for you sometimes? Ego.
Oh, yeah. Absolutely. I mean, I want to think of myself as a successful folder, right? That's yeah. Ego. I guess I like it that other people think of me as a successful folder. I have to admit that's fun too, but I'm not doing origami to get the external feedback. I'm doing it, for the internal feedback. I want to think of myself as a good folder.
Good point. Thanks for being honest. Yeah. And what could be the most important quality you have gained? Well, yeah, all this journey, and you still have this passion for origami. What's the most important quality you have gained and you have to maintain?
Well, a couple realizations. I mean, one is just that every field, it gets a lot more interesting once you get into it. I look at a field from the outside, and it looks like there's a few things you need to learn, and then that's all you need to know. And then as I get it, the deeper I get into it, the more and more I realize both what I don't know about it, but also what all the opportunities for discovering new knowledge are. And that's certainly been the case with origami. When I started down this origami path 50 something years ago, I had no idea that of what the possibilities were. And periodically throughout this career, there's been these revelations of new possibilities, new approaches in terms of complexity and beauty and application and functionality and so forth. But it's been a whole series of gains along the way.
Yeah, I really like this point about creating knowledge and to think about what could be possibilities. And maybe here a quick advice. Do you have any advice you can give to people who may be stuck in something? Yeah, it's as if they are fine with it, but maybe they have this passion for something. Maybe what advice you can give them to think about that, to be thoughtful about what they really, the real purpose is when it comes to what they really want to do in life.
Yeah, I kind of hedge, I'll answer this, but I want to hedge it up front.
Yeah.
That I was extremely fortunate to be in a position that I could take a risk of going off to work on a book for 2 years, and I had enough savings that that I didn't have to worry the way someone who might quit their job and then immediately have to start making money in the new field. It took me a couple years to build up an industry, to build up the new field. And during that time I had savings and I did consulting in my old field for a couple of years, like a day a week. And all that sort of helped the bridge. And not everyone is lucky enough to be able to do that. But I will say that it is possible to pursue a passion nights and weekends, as I did for many years, and be successful at it until the right opportunity comes along. And this comes back to one of my favorite sayings. It's almost my personal motto. It was said by Louis Pasteur, who said, "A chance favors the prepared mind," meaning that we can't predict what opportunities will come our way. We don't know when something will come along that we could jump on. But if we have prepared our mind, if we've learned about a lot of different areas, we've learned about the fields we're interested in, we have followed our curiosity in the past to learn about these different things, that when the opportunity comes along, we'll be prepared and then we can jump on it. And I think that is true for everyone.
That's absolutely beautifully said. And I can't agree more with that. This is really golden advice. Thank you for sharing this as well. And lastly, what was the best advice was given to you, and was the life changing? Was it personally or professionally? And was the life changing?
Oh, there were so many of those, but the one that popped into my mind right now was when I was in high school, and I was thinking about where to go to college. And I grew up in Atlanta, Georgia, and so I was thinking about Georgia Tech and University of Georgia and kind of local universities. And a family friend who had done his PhD at Caltech said, "You should look into Caltech. You're good at math. You should look into you should set your sights higher. Look for a goal that you stretch for." And so I did. And long story short, I applied to Caltech. I was accepted. My parents said, "Yes, you can go there." I went there, and that led to, well, a whole career. But I think it also revved up my mental engine to a higher degree than it had ever been revved, because it's a hard place. And it also instilled this kind of idea of how you go about analyzing a problem. You systematically break it down and you use math. And I did that in all my Caltech courses, and it led to that in my research and my laser career, and ultimately the world of origami.
That's also a good point. Yeah, to have these people in life to guide you sometimes to take a decision that may be life changing. So yeah, that's a good point. Yeah. And finally, do you have any final words you'd like to say for robotics and soft robotics community? Do you have any final words you would like to say?
Yeah, I'll say one. There's there is a lot of applicability of origami to the robotics community because, especially in the areas of mechanisms, we are both interested in things that move and things that move based on revolute joints. And in origami, those revolute joints are the folds, and in robotics, they're robotics. And so there's a lot that we can learn from origami and take to the robotics community. But those of us on the origami side of things need to be aware that the toolkit for robotics is far larger than folded sheets. And so more often than not, the best solutions are going to involve things that are not origami. So it's just one more tool in the box, but it's not a universal hammer where you treat everything like a nail.
Yeah, thanks so much, Robert. I think that was very inspiring. And again, such an honor to have you. And I believe you have a lot of things to say about origami. So hopefully we can have you again in the podcast and sharing more about your fascinating work. So thank you once again for being with us. Thank you.
Well, you're welcome. And thank you for this opportunity.